Hello, welcome to NPTEL online certification course on Introduction to the Application of Artificial Intelligence to Robotics. Today we are going to talk about decision trees and random forest method. So, these two methods which are parts of supervised learning we are going to see in detail today. The learning objective of today's lecture are I am going to explain you decision tree, root, internal nodes, leaves and branches. Then be seeing the classification and regression, you will be able to understand this. An example you will be able to work out, and you will be able to distinguish between the pre-pruning and the post-pruning operation. Then from the random forest you are going to understand the two randomization mechanism and how the random forest code works and what is the workflow. Okay, so here is the content. So first we are going to see the decision trees, okay, anatomy, classification versus regression, overfitting and pruning, and then internal logic rules and strength and weakness. For random forest we are going to see how these random forests are built and what are the again strength and weaknesses of the random forest. You see, decision tree is a supervised learning model and it is used for both classification as well as for the regression task. You see, they function as a hierarchical data structure, okay, that implement the divide and conquer strategy. I will be giving a little more detail about this. So, the divide phase basically means that the algorithm starts with searching for the best if else questions, okay, to split or divide the training data into the subsets, and the conquer phase means that the process continues until all points in the subset share the same level or the class, okay, or the stopping criteria is met. So, that is what is meant by the conquer phase. Let us see an example, okay. We are asked to distinguish between the four animals, say bears, hawks, penguin and dolphin. So, we could do it like this. First we can say that does they have feathers, okay. If it is true, then we can again question that can they fly. If it is true, it means that it is a hawk, and if it cannot fly, it means that it is penguin. Similarly, if has feather is false, then we can argue about do they have fins, okay. Then if it is true, it means it is a dolphin, otherwise it is bear. So, what it does, it actually it breaks down complex decision making into a series of simple, okay, sequential if else type of questions, okay, to reach a final decision. Okay, so if we look at the anatomy of a decision tree, okay, so every decision tree is composed of a root node, okay, and this is the very top node of the tree hierarchy. This is what we call as a root node, and this root node receives all end training samples and applies the first splitting test on the whole data set, right. So, then it has got edges, okay, often they are called branches like over here. So, these are called edges, okay, and they are directed lines that connect the nodes, okay, representing the discrete outcome of a test basically, okay. And then we have the internal decision nodes like this over here, okay. So, these are the decision nodes, and you see in a decision tree an internal node, also we call it as a decision node, okay. It is an intermediate level in the tree hierarchy that implements a test function, okay, in order to further split the data set. So, each node further split data set, okay, to guide it forward a final prediction, and these things can go on. So, what could be the test function, okay. So, the test function often say denoted as fmx, okay, acts as a local discriminant, okay. It is a basically mathematical rule, okay, implemented at each internal decision node in order to split the data into smaller and more homogeneous regions. So, based on the type of data which we are processing, okay, we could have a continuous features, alright. Now, in the case of continuous features, you see numeric feature, the test function, a comparison is made against a threshold, alright. So, for example, we can say that if say xj is greater than omega m, alright. So, this way we make a comparison, alright, say for FMX. So, this create an axis parallel boundary splitting the data into two branches, okay, and this is what we call as the binary split. So, you see in case of discrete categorical feature, here we have the non-numeric attribute, okay, such as say is the color red, okay, and the function checks for the specific value of that feature. So, this creates actually an n-way split and have one branch for each possible category. Okay. So, based on the use of number of input dimension, we can classify as the univariate, okay, which is basically you have only single input dimension, okay, and this creates an axis parallel boundary. For example, is say xj greater than 2.45 centimeter, or whether can fly like that, is the color red like that, okay. So, this way, and in case of multivariate, it's we have little more complex tree, and you see the test function can use all input dimension simultaneously, okay, and it often takes the form of a linear discriminant, something like this, say omega j xj plus b. So, for summed over j is equal to 1 to n, say this greater than 0. So, this type of thing, okay, and this allows data splitting using hyperplanes, okay, at arbitrary orientation rather than the parallel axis which we have seen in case of the univariate. Okay, and you see the algorithm chooses the specific test function, okay, that is most informative about the target variable. Okay. The goodness split is quantified by say for classification impurity measures in resulting branches, and for regression we minimize mean square error basically, okay, within the resulting branches. So, this way we can test the goodness of the split. Okay. So, the decision tree algorithm uses internal nodes, okay, and test function to recursively partition the input space into the localized regions, okay, and the process continues until data is separated, okay, into homogeneous group which we call as leaf nodes, okay. So, these are say leaf nodes, okay, and you see the what is a leaf node, this is also referred to as the terminal node, okay, where we have to terminate the process, okay, and so naturally it is at very bottom of the tree because your process gets terminated over there, okay, and there is no more further splitting is going to be, and this leaf node stores the answer, okay, made after a series of tests. So, for classification tree which is the majority class, and for the regression tree which is the mean or say average of the training instances, okay, that fall within that specific region. So, that is there. So, let us take here an example, okay. So, say we have feature 1, we have feature 2, and you have the two type of data, one is say blue and one is red. So, you see the each leaf node defines a localized region geometrically, okay, in the input space, and in univariate trees these regions are hyperrectangles, okay, formed by naturally axis parallel splits, okay. So, that is there, and in multivariate trees they can be more complex polyhedron, alright. So, when training instances reaching it share the exact same target value, that is what we call as the pure node, okay. So, here this is the pure node over here, it has got all the same target values. So, you have all blue dots over here, okay. These standard algorithm often continue splitting the data until every leaf is pure, okay, and through this there is a problem that we may encounter the overfitting, okay. We have discussed what the overfitting is in my earlier lectures, okay. So, the stopping criteria has to be there to control model complexity. Leaves are created when stopping criteria is reached, okay. What could be these stopping criteria? Say the maximum tree depth, okay, or a minimum number of samples per node, or when if I am further splitting I am not getting any significant improvement, okay. So, there we can stop it, okay. So, classification versus regression, okay, if you look at that them, you see both are hierarchical model, okay, implementing the divide and conquer strategy which we have seen earlier. Okay. The primary difference between classification tree and the regression tree is the nature of the target variable. Okay. They predict and the mathematical criteria used for partitioning of the data. So, in case of classification tree, what we have basically here we try to predict the discrete class level from the predefined list, okay, and output is typically a leaf node, okay, which corresponds to the majority class, and for the best split minimum impurity within the resulting branches is there. Okay, and in case of the regression tree, you see the goal is to predict the continuous numeric values, and the output of leaf node is usually the mean or say the average of the target values that is there. So, for the best split measure, the mean square error, okay, that is what we look for, okay. So, if it is there, then we have the best split. Okay. So, let us try to understand this concept using an example. So, say my problem statement is that I have got a humanoid robot, okay, and we need to have some fall detection and direction classification, okay, whether it is going to fall forward or it is going to be fall backward, okay, using the say inertial sensors, okay, which provides the vertical acceleration and the pitch rate. Okay. So, these the two input data are there. So, my data architecture has got input features where I have two inputs, one is the vertical acceleration and the other one is the pitch rate, and my output are three basically. Okay. I can classify at whether it is going to be stable or falling forward or falling backward. Okay. And say algorithm I am using the decision tree classifier, alright. So, you see the motivation for this is that unlike the black box logic and heavy matrix which we have seen in case of neural network and support vector machine, decision trees offer clear, visualizable robot behavior and faster real time response, okay. And as I said, the algorithm or the conditional logic here is simply that of if else. Okay. So, these are the code here. So, what we do, okay. So, here we import numpy basically, okay, because I have to do vector and matrix calculations. Then I import matplotlib, okay, for generating charts and subplots. Then from slearn import the decision tree classifier, okay, and the visualizer tool, that is the plot tree here. Then we import decision boundary display, okay, to plot classification boundary, that is region directly onto a 2D plane, and we can import train test split basically to split the data into the training and test data, and then import a listed color map, okay, to create custom discrete color map from the list of hex codes. Okay. So, I take a random seed of 42 here, a sample size 150. So, this random seed actually, as we have seen earlier, it is a fixed seed value for ensuring the same random data set are generated on every run, okay, and n is equal to 150, this is the data size, okay, variable to 150 per class. Then we generate n samples actually for the all the three classes, okay, using normal distribution, and output is going to be n comma 2 array, say acceleration in the z and the gyro reading about x, and with a pair of 150 data points for the each class, and then we can stack the three class of size 150 comma 2 into a single feature array. So, 150 for the each class. So, we are going to have the 450 for that, and then you have the output, okay, NP array. It creates the target table vector corresponding to the row of x, okay, alright. So, the machine learning pipeline for preparing data, training and deploying decision tree classifier looks like something like this. So, you have a data set basically. So, we split it into the training data set and the test data set, and then from the training data set we create a decision tree basically, where we are going to have the root node, we are going to have the decision node, okay, and then finally the leaf node we are going to have, after which we stop, okay. So, and then you have the final prediction. So, with this you see the major challenge with decision tree is that their tendency to overfitting, okay, and it creates a highly complex boundaries that memorizes the training data, okay, but if you are going to test it on new data, it is going to fail. So, that is the problem with that. So, there are two main strategies to combat this, what we call as the pre-pruning, and in pre-pruning basically we stop it based on any of these criteria, that is say we can limit the maximum depth, or we can limit the maximum sample leaf, or we can limit the maximum leaf node. That is the pre-pruning basically, okay. So, it involves stopping the creation of the tree before it is fully developed, and these are the common criterias. Alright, then we have other way of doing that is the post pruning, okay, or it is sometimes only called as pruning. Now, here what is done is that here the full tree build until leaves are pure, and then the algorithm evaluates each subtree, okay, and if replacing that subtree with a single leaf node, okay, does not increase error, okay, on the pruning set, the subtree is pruned. That is, I am going to check on the each node and making it a leaf node, alright, and then if my error does not increase, then I terminate there itself, alright. So, this is what is mean by the post pruning, and scikit-learn only implements pre-pruning, not the post pruning. Alright, so let us take that example which we were doing, we continue with that. So, here basically your X training, that is input for the training, and this is the input for the testing. Similarly, the output for training and output for the testing. So, this is the train test split basically. So, what it does, 70% is designated for the training and 30% designated for the testing. So, that we do, and then we train the pre-pruned model, okay, by decision tree classifier here. Okay. So, you see in a decision tree model objects, by setting maximum depth say as 3, we stop the tree expansion after the 3 level, okay, that is we are doing the pre-pruning, okay, and we train the model using the training feature matrix, okay. So, that way we do that. So, here is the output. So, here we can see that we have the accelerometer and the gyroscope data over here, and these are the 3 classification basically which we are getting. So, this scatter plot represents the physical space of the robot sensor values actually. You see this blot dot, this represents the stable one, the red dot is actually the fall forward, and the green dot is the fall backward. So, the different shaded background region represents the decision boundaries predicted by the tree over here. Okay. So, what could be the internal logic rules here? Okay. So, this flowchart represents the logic rules for the decision tree. So, here if gyro x reading is less than or equal to minus 45.452, so that is there, and then I take 315 sample and say this is the beginning, the class is considered a stable one, okay. So, if this is true, okay, then basically we classify that as the fall backward, and say if this is not true, then we set another criteria, that is say if this gyro value is less than or equal to say 61.097, alright. Then again 105 we have consumed here, so we are left with the 210, and again this one we classify as a stable one. So, then we take out this 105 sample and classify as a stable one, okay, or otherwise you are going to have this other classification. So, this is the actually the Boolean condition, and I have 315 training data set, which is basically the 70% of the total 450 data set, and these are my values, that is the class distribution is for stable, fall forward and fall backward, okay, and class is stable, okay, and these one what we call as the pure leaf node. So, let us look at the strength and weakness of the decision tree. Okay, you see the decision tree have 2 advantage over many of the algorithm, and that advantage is that we are able to visualize and able to understand the algorithm completely. Okay, and this algorithm is completely invariant to the scaling of the data. The weakness is what I have already discussed, the overfitting is the weakness, and lack of extrapolation, that is another weakness. Okay, so they cannot make a prediction outside the range of the training data. Okay, they simply predict the last known value from their leaves. So that is the weakness of this, and they are considered unstable, meaning small changes in training data can lead to vastly different tree structures. Okay, so people try to work on and the limitation of the decision trees, and they came up with algorithm which is called the random forest. Okay, so you see, random forest are powerful ensemble method, okay, that combines multiple decision trees in order to create a more robust and accurate model. Alright. So, what was the major drawback of the decision tree? We saw that the overfitting the training data. So, that was one of the major problem, and random forest directly addresses this limitation. Okay. So, this random forest originates from the two core concepts. Okay. One is the random, which means that we inject the randomness into the tree building in order to ensure that each tree is different and unique. And then the forest, that is the model, is a collection of these distinct decision trees. Alright. So, the fundamental idea is a single decision tree can perform well, but overfit the training data. A collection of trees, okay, is slightly different, can reduce this overfitting by averaging their result, and this is what is being done by the random forest. Okay. So, how this is built basically? Okay. So, you see, the random in the random forest comes from injecting two type of randomness into the tree building process. Okay. So, these methods are, one is the bootstrap sampling. Okay. So, here you see in bootstrap sampling for each tree, okay, the algorithm draws a bootstrap samples from the N sample, okay, training data by randomly picking N samples with replacement. Okay, a replacement means we may use the same number again, alright, okay. So, that is there, and this results in a data set of the same size at the original, but with approximately 1/3 of the data missing and other point repeated. So, here is the example. Suppose my data set is like this 1, 2, 3, 4, 5. Okay. So, the possible bootstrap sample could be say 2, 5, 3, 2, 5. You see, so here 2 is being repeated, 5 is being repeated, 1 is not at all there, right, or I could have say 3, 1, 1, 4, 3 like that. So, here my 3 is there, 1 is there, 2 and 5 are not there. Okay. So, this way we generate the random data. Okay. So, next the decision tree is built on the newly created data set. Okay. However, the algorithm we described for the decision tree is slightly modified. Alright. The second method is the feature randomization. Okay. So, here you see in the feature randomization, instead of searching through all possible features for the best split at each node, this algorithm randomly picks up, okay, a subset of feature and find best split among them. So, the number of features for this subset is controlled by the max feature parameters, and you see this selection of a subset of feature is repeated separately in each node, so that each node in a tree can make a decision using a different subset of the feature. Okay. So, the bootstrap sampling ensures that each decision tree in a random forest is trained on slightly different subset of data, okay, with the same size. Simultaneously, the feature randomization, where we are picking up some selected features, okay, forces each split within a tree on the random subset of features. So, together these two mechanisms ensures that all the trees in the random forest are different. Okay. So, how this random forest makes the prediction? So, what algorithm does is it first make a prediction for the every individual tree in the forest, then for regression we average the result to get the final prediction, and for classification we use the soft voting strategy. Okay. Now here you see each tree provides a probability for each possible class level, okay, and then these probabilities are averaged and the class with the highest probability is predicted. So this is how we do for the classification. So the flow chart looks like something like this. So we have a data set. So we split that data set into the training data set and the test data set, and from here this is my decision tree 1. So likewise I can have say n number of decision trees. So I have n prediction for the tree n, and then I can have the final prediction. Okay. So this is how the flow chart works for this one, okay, and this is what we call as the random forest. Okay. So if you look at the code for this, so as learned here we get import the random forest classifier here. So load data set, split data set into training and testing, and here number of estimators, say we select some 5 estimator here, okay, and these set the number of trees to build for random forest regressor or for the random forest classifier. Random state 2 logs this randomness for reproducible results, and the max features by default algorithm uses SQRT, okay, that is the square root of the total features. From that we can get the max features. So if you have the 2 features, square root of 2 is going to be 1.414. So we can have the maximum 1 feature. Okay. So the output, the decision boundaries say found by the 5 randomized decision trees could be like this. So this is for tree 0, tree 1, tree 2, tree 3 and tree 4, and then the decision boundary is obtained by averaging their predicted probabilities. Okay. So we could take the average of that, okay, and then based on that we can get the final prediction, right. So here you see this part, here you have blue, here also blue, here also blue, here some part is blue, some part is red, here some part is blue. So you average it out, so you will be getting this part. So that is how this comes to the blue region, okay. Otherwise we can classify here, okay. So coming to the parameter strength and weakness of the random forest, you see the number of distinct trees to build, generally as many as you have the time or memory, okay. So that is the, as if you are going to have the more number of trees, that is going to reduce the overfitting. Then we can select the maximum features. This controls how random each tree is, okay. The default values for the maximum feature is square root of n feature. This is for classification, and for regression this is the log on base 2 of the number of features. The strength is the performance and robustness. Okay. You see the random forest nearly always perform better than the single decision tree, okay, and often work well without intensive parameter tuning. Okay. Then there is scaling invariance is there, like single tree they are invariant to the scale of the data and do not require pre-processing such as normalization or standardization. Then parallelization is there. The construction of trees is embarrassingly parallel, meaning it can be easily distributed across multiple CPUs, okay, cores. So that we can do. The weakness is the more memory and the slower to train and predict than the linear model, okay, do not tend to perform well on high dimensional data. Okay. So again like all tree based model, they can also cannot extrapolate, okay, or make prediction outside the range of the training data. So to summarize, you see the decision tree is more intuitive, okay. So and most robot decisions are based on if then rules, okay. It's easy to interpret and visualize, alright. We can control it by maximum depth, minimum sample leaf and pruning operation. Then the random forest we have seen, it's a very powerful, okay. So we can have entries, we can have bootstrap sampling, and the random feature subset which we have seen, we can have that, okay. We have lower variance, higher accuracy, okay. So that is there, but again this takes lot of memory and slows the processes. The robotic application of these two methods could be say terrain classification for the mobile robot, then fall detection, okay, UAV navigation, all this could be there, alright. So decision tree for quick prototyping and the random forest for the production deployment, and these are the references, okay. Most of the material we have taken from the first text, Introduction to Machine Learning with Python, okay. So that you can look at, and thank you, see you in the next lecture.